All right, welcome back to Mr. P Helps with Calculus. We have Unit 5, Day 3, and we're talking about MVT, the mean value theorem. And honestly, this is really kind of an easy theorem once it makes sense to you, which I'll try my best to help it make sense for you. All right, so we're going to look at, here's what MVT basically states. It says that if f of x is a continuous function over a closed interval, kind of like EVT, has to be continuous, has to be on a closed interval. And here's the difference. It must also be differentiable at every single point over that entire open interval. Actually, it doesn't have to be differentiable at the endpoints, but that rarely ever happens. Then there is at least one point C in that interval from A to B in which the instantaneous rate of change must equal the average rate of change, that mean rate of change. So that's why we call it mean value theorem, that the average rate of change has to be equal to the derivative, or the average rate of change has to be equal to the derivative at least one place over the function. Now, it could happen more. It could happen 2, 3, 4, 5. Technically, it can happen an infinite amount of times, and I'll show you why that is in just a moment. All right, so let's say we have a function, and the pink is the function itself. And it could be anything, and it has to be over a closed interval. It has to be continuous, and it has to be at least differentiable over the open interval. Those are the rules that we just stated for MVT to be applied. Now, what it's basically saying is that whatever the average rate of change is from start to finish, and that's what this blue line represents. The blue line is the average rate of change, and in this case, I just made up a number. I said it was up 1, right 2, up 1, right 2, up 1, right 2, but technically it could be anything. So whatever this average rate of change is, and that's the mean, and you would normally use, slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That rate of change has to occur at least once over the function somewhere in between the start and end, somewhere between A and B, and we just call that C. It has to have that exact same tangent line slope, meaning the tangent line's parallel to the average rate of change at least once. Now, you'll see that I've kind of already drawn that it looks like it happens twice. It happens here, and it happens here. So this green line is parallel to the blue line because the average rate of change is the same as this tangent point. So the blue line was the average rate of change, and this green line happens to be the tangent at point C. And it happens to also be parallel to this point right here. And that's all that MVT is basically saying. That if a function is continuous and it's differentiable over the open interval, then it must have the exact same slope at least once somewhere in the middle of the function. That's essentially what this is basically saying. All right, so now, in order for MVT to be applied, it must have all of that criteria. And on the AP exam, you must state that, as I've stated here on the paper. And this is kind of an example. Keep in mind, you don't have to write it exactly like me. You just have to have the same information included. Show that f of x equals x squared satisfies the hypothesis for MVT on the interval from 0 to 2. That is a closed interval from A to B. Then find C. Okay, so we're actually going to find the place where it does end up being exactly the same. Now, first rule is that the function must be continuous. You have to state all this. It is also differentiable over the interval from 0 to 2. Technically, it doesn't have to be closed, but it is. Therefore, MVT does apply. Yes, you must actually physically state that MVT has to be applied. Now, you don't actually have to write mean value theorem. You can assume, just like IVT or EVT and all the other theorems, that you can assume whoever's reading your answer knows what MVT stands for. All right, so what it basically states is that the average rate of change has to equal the derivative at least once. Now, it could happen more than once. So what we're essentially going to do is just plug in all the numbers. So we're going to plug in to find the average rate of change by finding f of 2 minus f of 0. Remember, this is the interval right here. And we can find those numbers by simply putting the numbers into the function. 2 squared, and minus 0 squared. 4 minus 0 happens to be equal to 4. Divide that by b minus a, which is 2, and you end up getting 2. That's the average rate of change. From start to finish, it's going up to right 1, up to right 1. Well, it's actually only doing it once, but I digress. Now, that average rate of change, which I go back to that happens to be the blue line I already did. This is the blue line. Everything on the right-hand side has to have the same rate of change at least once on the derivative. So the derivative represents the rate of change at any given point on the entire function. So that's f prime of the function itself. Well, that's pretty easy because x squared, the derivative would be 2x. Well, in this case, we're going to use c to represent it. So 2c, because c just represents any time over the interval where the derivative happens to be the same. So we set it equal to 2c, and it happens to be c is equal to 1. So we now know that after 1 second, the average rate of change is exactly the same as the tangent line at that given point. Now, this is just me showing the work of what I just did a second ago. Yeah, I did use c to represent x in this case, and that's how I plugged it in. All right, let's take a look at another one. It says, given this function, use MVT to find the value of c over the interval from 0 to 2. Once again, f of x is continuous because this is cubic, and cubic functions are always continuous. And they are always going to be differentiable in this case as well. There are no corners, no cusps, no vertical tangent lines. Therefore, MVT does apply. So once again, we're going to say that the average rate of change, that's what MVT states, is that the average rate of change will have to equal the tangent line at least once over that given interval. So I take the function itself, find the derivative, set it equal to the average rate of change. So that's what I've done over here. So 3c squared minus 1 is the tangent line equation. Set it equal to the average rate of change, and then just solve for it and keep solving until you find what c ends up being. And it looks like we get both positive and negative square root of 4/3. And I would just leave that as the answer. Now, the reason why I've wiped out, and I'm just going to leave it to just the positive answer, because negative square root of 4/3 is not on our closed interval. So that's the reason why I did not circle this as my answer, because only the positive one is on our interval. Otherwise, if this interval was from negative 10 to 2, then we would have included both of these answers. All right, sometimes MVT cannot be applied, and those are actually kind of the easiest questions because all you have to do is state why it cannot be applied. So in this case, we have x to the 2/3 power. You know anything to a fractional power is going to give you these cusps. So anytime you have a cusp, therefore, it is not differentiable at 0. Now, just because of that doesn't mean the MVT can't be applied. We have one more thing we have to check. 0, which is the cusp, has to be over the closed interval, which it is. In other words, what I'm trying to say is, had this been from 0 to 3, had that been the closed interval, it would have been continuous over that entire closed interval, and it would have been differentiable on the on the open interval, because 0 does not have to, the endpoints don't have to be differentiable. Only the points in between the endpoints have to be differentiable. Now, had this been the interval, then yes, MVT could have been applied. But since 0 is in between -3 and 3, therefore it cannot be applied because it is not differentiable at 0. As we've learned with our discontinuity, just go back to that video if you need a refresher. All right, once again, x to the 4/5 is going to be a cusp. But let's just check. Oh, this is tricky here. This is the exact trick I just went over a second ago. 0 does not have to be differentiable because it's only over the open interval does it have to be differentiable. So over the closed interval, it has to be continuous. And yes, this is continuous. And it is differentiable on that open interval. So yes, MVT can be applied. And that's kind of a tricky situation where the endpoint was not differentiable. So we go forward and we find our derivative, just like you use your power rules. And then you would set it equal to the average rate of change and then simply just solve using your algebra skills. I'm not going to go through it step by step, but you can clearly see I've shown all the steps to show the algebra. And then in the end, you get your answer. And remember, you do not have to simplify your answers. You can leave them as long as the rule is if you can put it in a calculator, then you can leave it. And that looks to be our last example. Thanks again for watching, and I hope you learned something from it, and I'll see you on the next one.